Welcome everybody to the One Word Mathematical Physics seminar organized by the International Association of Mathematical Physics. And our today's speaker is Simone Rademacher from the University of Mannheim, and she will speak about the long-time validity of Bogoliubov theory. So please, Simone, go ahead.
Thanks a lot for this very nice introduction and also for giving me the opportunity to present some of my research that is joint work with Phan and Avi Soffer here in this seminar. So as was already said, I will talk about the long-time validity of Bogoliubov theory. So Bogoliubov theory is a theory that was introduced by Bogoliubov in the 1950s for the effective description of quantum fluctuations in Bose-Einstein condensates. So let me first give a brief idea about what this effective theory is about. Right, perfect. Let me make this one maybe a bit smaller. Okay, so the study of Bose-Einstein condensates is a very active area in both in mathematics and in physics. Okay. So it has been on one hand analyzed from the mathematical point of view, but also from the both from the physical and the mathematical point of view, how these Bose-Einstein condensates behave or how to describe them. So this goes back on first theoretical prediction by Bose and Einstein. So this is also where the name comes from. And what they described was that Bose gases at very low temperature exhibit a phase transition. So when they are cooled down to very low temperature, most of the bosons, so of a gas of, for example, of atoms, condense into the same quantum state and behave as a unique quantum wave. And this was realized physically in experiments later on by working groups of Ketteler, for example. And what they did, so this is from their experiments, is to trap a Bose gas or a gas of rubidium atoms, cool it down to very low temperatures, then release the trap and measure the velocity distribution. And their result you can see in this picture here. So what they found was like a central peak. So this is so basically that's the condensate behavior, which you can see here. So but what they are able to do now, since or more recently, since they have now better techniques in their experiments, is that they cannot only see the response of the condensates when they perturb the system with a momentum q, but they can even see the response of some fluctuations around the condensate that you can see, for example, here in this picture. And these additional fluctuations they see in the experiments are they called them or they identified them as the so-called Bogoliubov excitations. So on fluctuations that they find around these condensates behavior, right. So this is from the physical perspective, and what we are interested in this talk now is now about the mathematical description about this phenomenon. And to be more precise, what we aim for is a mathematical framework in which we can show that these fluctuations around the condensate behavior are in fact effectively described by a so-called Bogoliubov dynamics for all times. Right. So that's the goal for this talk. And how to do that is I will describe given or based on the following structure of the talk. So first of all, I will set up the mathematical framework that we need to be then able to state our results. That later on, I will compare also to the literature, because as I said, like the study of fluctuations or more generally about Bose-Einstein condensations is a like very active area in mathematical physics. So it's very important to compare it also about with the existing literature. Then I would like to sketch the idea of the proof and also emphasize what is novel about our result here, and give an outlook about what we are, like, starting from our result, we are interested in analyzing in the future, and what we can say more about that. Right. So let me start with the mathematical framework that we work in to describe those Bogoliubov excitations. We want to describe the Bose gas, so the dynamics of this Bose gas, so more or less describe these experiments that the physicists were doing. And mathematically, we do this by considering n bosons that we realize in the Hilbert space L2, L2S, which is the symmetric subspace of L2 functions in and here we consider bosons that live in 3 dimensions, so of R3 to the n. And in fact, the dynamics by the basic principles of quantum mechanics is given by the solution of this Schrödinger equation here. And we consider a very special class of initial data. Namely, we consider initial data that is of these forms. So initially, we have all the bosons in the same state, which means we consider the purely factorized state phi 0 to the n. So initially, it's very clear that we do have Bose-Einstein condensation, in like even in very strong sense, because in fact, all the particles are in the same one quantum state. However, now we consider the time evolution of this factorized state, and then we cannot expect that this factorization is preserved over time, because the Hamiltonian we consider is the following. It's a sum of 2 terms. So on the one hand, here we have the sum of all the Laplacians, delta I, that act on all the I particles. So I runs from 1 up to n. And we have an interaction term, and this interaction, you can see here, it's a 2-body interaction. So it depends on the distance of the ith and the jth particles. So the sum of the interaction runs over all indices I and j from 1 up to n. And in order to make both terms compatible, we choose the coupling constant to be here 1 over n. This scaling regime is also in the literature referred to as the mean field scaling. So one expects the particles to experience a large number of weak interactions. That's the idea behind. And so this system in the setting was analyzed already in the literature quite a lot, and it is actually known that this system exhibits, or this wave function exhibits, Bose-Einstein condensation in the mathematical sense. And with that, I mean that the one particle reduced density matrix matrices, which I denote here with gamma and t. So this is right. That's the usual. So here I use the usual definition of the one particle reduced density, where one traces out every particle starting from the second up to the nth. And it was proven that in the large particle limit, so for n to infinity, this converges to a projection of a one particle wave function phi t. And this one particle wave function phi t solves the following nonlinear Schrödinger equation. So these nonlinear Schrödinger equation, you can see here, it's also known as the Hartree equation. And you see that there's a relation between these Hamiltonian here and these nonlinear, this Hamiltonian here, in the sense that this interaction term is replaced by this mean field interaction you find here. So this convergence was proven in trace norm, and for suitable assumptions both on the interaction potential V and also on the initial state phi 0. As I already said, so there's a wide list of references for that consider different cases or different situations for both the potential and the initial data. and also had different focuses on either improving the rate of convergence or the time validity of these approximations here. Right. What we are interested in now is to go a step further, because we want to analyze the fluctuations around these condensates behavior. So that's the goal for this talk, that we want to analyze the quantum fluctuations around. And to do that, we first need to introduce a bit more mathematical notation to be able to extract the fluctuations that happen outside or around these condensates behavior. And the idea that we want to use here in this talk is the following, namely that we can decompose our wave function psi t, that is the solution of these n-body Schrödinger equation, in the following way. So we decompose it as products of the condensate wave function and functions psi t, j, which are orthogonal to products of the condensate wave function. And then here we sum over all possible combinations one can do with that. And the idea is that we want to study now the fluctuations by analyzing these functions here, psi t, j, which are orthogonal to products of the condensate, because they represent exactly all the fluctuations, or all the fluctuations, right, which are not in the condensate. And we can group them together as a vector that psi t0 up to psi tn, where psi t0 has 0 particles and psi tn has capital N particles, which means I can understand this vector to be element of a so-called truncated Fock space. I hope most of you are familiar with these Fock space notation, because this truncated Fock space is special because of two things. So first of all, I mean, this is where the name comes from. It has a truncation. So it is built with respect to a special class of L2 functions I comment on later. But then we sum up here only up to the capital N-fold product of these L2 space. The reason is that we initially start with a wave function that has a fixed number of particles, so n particles. So whenever we study now fluctuations of these wave functions, we cannot have more than n of these fluctuations. So for that reason, also this vector here cannot have more than n fluctuations, which we, right. So it is an element of these very special Fock space, because the usual Fock space, as I guess most of you, or all of you know, has elements which also might have an infinite number of particles. So the sum is not truncated, but runs up to infinity. There's a second property of the truncated Fock space, which is very special. And this is that it is built with respect to very particular class of L2 functions, namely L2 functions which are orthogonal to the projection onto the condensate. And this is this I denoted here with these perf phi t. And again, this is simply by construction, right? Because here what we started from was this decomposition here, where we asked all these functions psi tj to be in fact orthogonal to products of the condensate. Okay. Right, so now we have these vector of fluctuations that we want to analyze, which is element of this truncated Fock space. However, for our analysis, what will be important that in fact we can embed always these very special Fock space in the standard one. And for the standard Fock space, we have, for example, the standard notion of creation annihilation operators, A star x and A y. So A star x is the creation operators that creates a particle. AY annihilates a particle, and they satisfy the standard CCR that you can find here. Right. Right. What it was proven in a paper by Levin, Serfati, and Soloway that in fact there exists a unitary UNT that maps these n particle wave functions sin t to these excitation vector here. Which means that if we want to analyze now the excitations or fluctuations of our solution of the Schrödinger equation psi and t, what we want to do is to, in fact, analyze these excitation vector through applying these unitary u and t to our psi and t. Right, so this is the right quantity we want to consider now, and we want to find an effective description for. And for that, it makes sense to rewrite it a bit in the following sense, namely, we want to, so we artificially added here using the fact that un is in fact unitary, sorry, un star 0 and un 0, which we can do, right? Otherwise, nothing happened. I just rewrote psi and t as the exponential of the generating Hamiltonian times the initial state psi and 0. And now we want to use the fact that we, at least for our result here, we consider a very special initial state. Namely, we consider the initial state that was the purely factorized state, right? So we this was phi to the n. And if we have, again, a look on the definition of our unitary here, we see that un, especially at time 0, maps to everything that is orthogonal to products of the condensate. However, if we start with something that is a pure factorized state, so a pure condensate, this simply maps to the vacuum, which means that these yellow guy here simply is the vacuum, right? So that one here is the vacuum. And the remaining part here we call the so-called fluctuation dynamics. So what we want to do, or what our main result is about an effective description in the large particle limit n to infinity of exactly these fluctuation dynamics W and T. So that's the goal, that we want to effectively describe that. Right. So how to do that? Here I just copy pasted again the definition of the guy we want to analyze in the large particle limit. And as a first observation, it's very easy to see that at time 0, I mean, these exponentials simply is 1, and we only have here the unitary un 0 times un star 0, so it's a unitary, which means at time 0, this is simply the identity, the fluctuation dynamics. For positive times, we can compute the generator of the time evolution of our fluctuation dynamics that is given by this following formula here. Namely, when we take the time derivative of these, the fluctuation dynamics defined like that, on the one hand, we have to compute the time derivative of the unitary u itself, which is done here. And on the other hand, like when taking the time derivative, we get down the Hamiltonian Hn. So we have to compute the conjugation of Hn with our unitary u and t. So these are these two parts we have to compute to get the generator of the fluctuation dynamics. And the good news is that one can do that. So it's a lengthy computation, but one gets an effective description and these an explicit expression. And these computation is based on the following ideas. Namely, first of all, as we already saw in the previous slide, the idea is that we want to embed everything on the Fock space. So first of all, we have to rewrite our n-body Hamiltonian as an operator on the Fock space, which we can easily do. And we see that, again, there are these two parts, right? So, sorry, on the one hand, we have the kinetic energy that is quadratic in creation annihilation operators, A star x, A, y. And then we have the interaction term that is quartic in creation annihilation operators, but comes with a 1 over n in front. In particular, one sees here from or on these expression for Hn that the expression is written basically in pairs of creation and annihilation operators. And this is good news because in the paper of Levin, Klein, and Safferty, what they showed that there are some explicit rules how the unitary un acts on pairs of creation annihilation operators. And in fact, it acts as the following. So whenever we have pair of A star phi t and A phi t, then the unitary maps this pair here to capital N, so the total number of particles, minus the number of particle operator on this truncated Fock space. So, which is called n plus of t, and is exactly the operator that counts all the excitations, so all the particles which are not in the condensate. Moreover, we also know how it acts on a pair of a creation operator of a function f that is chosen to be orthogonal to the condensate, and A of phi t, which is the condensate. And in fact, this is mapped to A star f times the square root of the total number of particles minus, again, the number of excitations. Right, so the idea behind is that the right-hand side is something that is really an operator on this truncated Fock space, because you can see that the right-hand side cannot map outside the truncated Fock space. Because whenever you apply this one here to a state that already has capital N excitations, the square root vanishes. So you cannot create excitation above capital N excitations, which is nice. And another intuition one can get from this property here is that usually one or intuitively one should think of these number of excitations to be much smaller than the total number of particles n, which means that at least for large n, we can think of this square root behaving like the square root of the total number of particles. And in that sense, this unitary replaces this creation operator, annihilation operator of phi t simply by the square root of n, which is something which is also sometimes known as the C-number substitution in physics. So somehow this unitary is related to this a mathematical version of the C-number substitution in physics. Right. And also, like now since we know these properties here of this unitary, as I said, one can like do straightforward computations and in fact get an explicit expression for these generator of our fluctuation dynamics. So I'm not commenting much more on the precise calculations, but we will have a look about the result that one gets in the end. And this looks like that. So this generator L and T turns out to be the sum of two parts. So on the one hand, we have a Hamiltonian HT that is independent of n. And on the other hand, we have something that we call the remainder, and that we hope to be able to show that is small in the end and comes at least with a 1 over square root n in front. And since we are interested in the large n limit, we have hoped that this one is small compared to the first one here. And these Hamiltonian HT, this is precisely the so-called Bogoliubov Hamiltonian that we were hoping to derive for as an effective description in the end. And it has two special properties that are important here. So the first one is that it is n independent of n. So we there's hope we get an n independent limit in the end for our fluctuations. And the second is that this Hamiltonian is quadratic in creation annihilation operators. On the one hand, we have here this term that is the gamma, which is the second quantization. So it comes with a star x and a y. And on the other hand, we have a term here that is that comes with two creation or two annihilation operators. Also, like in this definition of this Bogoliubov Hamiltonian, there are a couple of operators that I wrote down below here in this footline. It's maybe not so important to know how they precisely look like, but what is important to know is that we have an explicit expression for them, and they only depend on the potential and the solution of the Hartree equation, so the condensate's behavior. Right, so this is this leading order Bogoliubov Hamiltonian, and then we have the remainder terms. And so there's a long list of remainder terms, and I only listed two of them to get an idea how they look like. And as you can see, they, at least the ones listed, they are at least cubic in creation and annihilation operators. So that one is cubic. Here we even have a quartic term. So they are higher order in creation annihilation operators than these Bogoliubov Hamiltonian is, and they still do depend on n. Right. However, they have these, or at least have a prefactor of 1 over square root n in front. So that's the reason why we have hope to show that, in fact, this remainder term is a remainder, so that we can neglect it in the large particle limit. And that's the goal. So this is also what our main theorem will be about. Namely, we want to compare these fluctuation dynamics that we were discussing before, which is an effect, which is the description for the fluctuations we are interested in, and is defined on this truncated Fock space by a so-called many-body Bogoliubov dynamics, which is the dynamics that has exactly these Bogoliubov Hamiltonian we saw on the previous slide as a generator, and which we call U2 in the following. So the reason for this 2 is because it's quadratic in creation annihilation operators. And in contrast to the fluctuation dynamics we started with, this Bogoliubov dynamics, however, is defined on the full Fock space and not on the truncated one. Right. One might think that maybe this makes our life more difficult because, I mean, the truncated Fock space is nice because it's truncated, so we can have not more than capital N particles. And now if you approximate it with the Bogoliubov dynamics, we actually end up with something that is defined on the full Fock space. So it might be harder to like discuss properties or study things there. However, these Bogoliubov dynamics has very nice properties, which in fact make it very easy to analyze and compute things there. And this is something that can be proven, and is proven, that to every many-body Bogoliubov dynamics, there exist associated operators gamma t and sigma t, which are operators on L2 only, and they are bounded. And they are given by this, and they allow to effectively or to compute effectively the action of these many-body Bogoliubov dynamics on creation annihilation operators. With that, I mean the following, namely the conjugation of an annihilation operator A of f, where f is an L2 function, with a many-body Bogoliubov dynamics, is given by this expression here. So it's sort of a rotation. So because this is mapped to A of gamma TF plus A star of sigma TF. And these operators gamma T and sigma T, we have, we can, or are often grouped together in these matrix theta, and theta TS is then called a symplectic Bogoliubov dynamics. So the idea behind is that we start with these many-body Bogoliubov dynamics on the Fock space. However, whenever we want to actually compute things with respect to this Bogoliubov dynamics, it is in fact enough to study these symplectic Bogoliubov dynamics, which is a dynamics on L2 plus L2 only. So much easier to analyze. And in fact, we even know a lot about these operators gamma t and sigma t, so it's really enough for most of the things to only discuss these symplectic Bogoliubov dynamics instead of the many-body Bogoliubov dynamics. Because, so this is the next slide about because basically from these, or from the definition of these many-body Bogoliubov dynamics, one can show properties of the symplectic Bogoliubov dynamics, and these are given by the following. So first of all, we know that initially, so gamma t of t, simply given by the delta, by delta of x minus y, and initially, so sigma tt is simply equal to 0. And we even know how the evolution of these operator theta looks like. Namely, the evolution is given by the operator Ts, and Ts is the following matrix here. So in the diagonal, you can see it's the Hartree Hamiltonian plus the K1s operator that already appeared in the definition of the many-body Bogoliubov dynamics. And in the off diagonal, you see this operator K2 appearing. That was also already there in the definition of these many-body Bogoliubov dynamics. So in fact, these operators that are in the diagonal of these matrix theta are the terms that appeared in the diagonal term of the, so the diagonal term meaning the term that comes with the A star X A Y of the many-body Bogoliubov dynamics, and these off-diagonal terms were in the one that came with two creation or two annihilation operators. Right, and so this dynamics feature is not self-adjoint, however, is in the literature is often denoted as a symplectic Bogoliubov dynamics, so one still has very nice properties for that. And very often, whenever one discusses these many-body Bogoliubov dynamics, it turns out that it is enough to analyze or to study these symplectic Bogoliubov dynamics and prove things for them, and then lift them to the many-body dynamics. And this will also be the crucial ingredient for our theorem that I will now finally be able to present on the next slide. Okay. Right. So now we are finally, after all these notation and discussion about fluctuation dynamics and Bogoliubov dynamics, we are finally able to state the result. That is the following. So this is a result together, as I said, with Phan and Soffer from last year. And we proved the following thing. Namely, we compared these excitation vector, which is exactly these fluctuation dynamics applied to the vacuum, discussed on the last slide. And we compared this one to these Bogoliubov approximations, so to the Bogoliubov dynamics applied to the vacuum. Both are normalized states. So we proved that the difference of their norm is small in the sense that we can bound it by a constant uniform in time over n. So whenever n is large enough, this is in fact a good approximation. Right. So here we considered the Fock space norm, as I was saying, because this is a vector that lives on the Fock space, and we can always embed this one also to the full boson Fock space. Right. To get this result, we had to put quite strict assumptions both on the potential and the initial data, namely the following. So we had to require V, so the potential to be in C 0, 2, and also to be non-negative, radially symmetric and decreasing. And also the initial state phi 0 needs to be in W1L for large enough L. And why that is because we needed to make sure to have some dispersive behavior of the condensate wave function, so of phi t. So we put ourselves in a situation where we can apply dispersive estimates that were proven, for example, by Krylakis and Macedon in 2017. And with that, I mean the following, namely they proved that the L infinity norm of phi t is bounded by a constant over 1 over t to the 3/2 for all times. Right. And so this is known as a dispersive behavior in the literature. And the idea behind, I try to sketch in this picture that hopefully you can see here. Sorry. So what I try to plot here is the density of the solution of the Hartree equation. So it's the norm squared of phi t of x. And the increasing time is indicated with the color. So the darker the color is, the larger the time is. So initially, the time that's indicated with the yellow line, the density is very much peaked. But then the larger the time is, the more the density spreads out in space. And this is exactly denoted or like mathematically quantified with this estimate here. Right. But we needed more. Like, in order to prove this result for these approximation of the fluctuations, we did not only need dispersion of the solution of the Hartree equation, but we even needed a dispersive behavior formulated in the right sense that I will comment about later, of the symplectic Bogoliubov dynamics theta. And this was something that is, at least up to our knowledge, completely new and not known from the literature, that one even has dispersive estimates, so some decay in time of these symplectic Bogoliubov dynamics. And in order to ensure that, we needed to put some more assumptions on the potential, because in order to get these dispersive estimates for the Hartree equation, at least Grelakis and Macedon only proved it for V in C1. And in order to get this now also for these symplectic dynamics, we even needed V to be in C2 to be right. Okay. As I mentioned before, the study of Bose-Einstein condensation, and not only Bose-Einstein condensation, but also the fluctuations around, is something that is widely done and in the literature. So let me compare our result to the existing literature. So first of all, for the derivation of the Hartree approximation, so in the sense of the convergence of the reduced one particle density, a uniform in time estimate was derived by Li and Dietze in 2023, and also quite recently in a bit different situation by Zhong, Li, and Sun. So the idea there for deriving the Hartree approximation, so the description of the condensate, is that one has to very carefully do the estimates on the Fock space, and then use the dispersive estimates for the condensate, so for the Hartree equation, for example, by Grelakis and Macedon. Right. So for this Hartree approximation, it seems that it is enough that one knows that the condensate itself has dispersive behavior. However, if one wants to go a step further and now analyze the fluctuations around, it turns out that this dispersive behavior of the condensate is not enough. And so this effective description for the fluctuations by this Bogoliubov theory or Bogoliubov approximation that we now also discussed before was proven before for smaller time scales. So the first results by Levin, Nam, Schlein, and later on also by Nam and Napiorkowski, Mitruskas, Petra, Pickel, and Bosman, Petra, Pickel, and Soffer, they mostly consider, or all of them were only for time scales which are logarithmic in n. And then there was later on some works by Grelakis and Macedon, so the one I already referred to before, and also by Nam and Piorkowski in 2017, that were able to increase the timescales from times which are logarithmic in n to times which are at least now like square root n. So what is now new in our result is that in fact we get something that is valid for all times independent of n. But as I already said, for that we needed crucially new ideas, and we needed to prove some dispersive estimates, so some time decay in some sense of the symplectic Bogoliubov dynamics, which was not done before. And so why that? So my next slide will be about what goes wrong if one does not use, or what are the difficulties in improving, in fact, the timescales. And this we can pretty easily see if we start like naively with the basic, like one of the basic idea that most of the papers that I was referring to before use when trying to prove such a norm approximation. Right. So what we want to do is to compare the following two guys. So on the one hand, we want to compare these excitation vector with the Bogoliubov approximation here. And what we do is to use Duhamel's formula. So we write it as a time integral of the derivative of this guy here. So what we get is the time integral of the time derivative of the scalar product of our excitation vector with this Bogoliubov approximation. And in fact, this is something we already saw, that this excitation vector we can also rewrite as our fluctuation dynamics applied to the vacuum. So now we have to compute the time derivative of the scalar product, which means on the one hand, we get the time derivative of the left-hand side minus the time derivative, and the time derivative of the right-hand side, which we can compute. So this is exactly this difference of our generator of the fluctuation dynamics minus the Bogoliubov Hamiltonian. And the difference of both of them, this is something we saw some slides before, is exactly with these guys which are called the remainder term, where we were hoping that we can prove that this is small. And in fact, let's focus here on one of the remainder terms, namely that one that is quartic in creation annihilation operators. This one here. In fact, it turns out that at least for the time, in order to improve time scale, this is in fact the most difficult one. And the reason why, maybe for those of you who are a bit familiar with those Hamiltonians, is that all the other remainder terms, they at least come with one factor of phi t, so with one factor of the solution of the Hartree equation. And this helps, at least for a time scale reason, because we know, or because of the assumptions we put, we know that we have dispersive estimates for phi t, so we do have some decay in time, simply from our remainder term. But the problem with this guy here is that we don't have any factors of the condensate, which means we cannot hope that we to get some help basically through phi t. Okay, so let's start with that. So what can we do? The idea is, or very naively estimate this one here by standard techniques, because for those who are familiar with Fock-based techniques, I guess they know that one thinks of one creation of annihilation operators to basically scale like the square root of the number of particle operator. So naively, one could estimate this guy here by the square of the number of particle operator, which is here applied to the Bogoliubov dynamics on the right. And because of commutation relation, one also gets like another number of particle operator here. This seems to be okay because, as I said, we because of these special properties of the Bogoliubov dynamics, we can actually show, or it's very easy to show, that the number of particle operators and in fact any power of the number of particle operator one can bound by a constant uniform in time. So those guys we can bound by a constant c. All right, so let's do that. So that's these constant c here that we get. And this seems good on the first look, but then the problem is that we still have to do a time integration here, right? So if we do all these very naive estimates, what we would get is an estimate that is linear in t, so linear in time. And this was too bad because we wanted to have something that is in fact uniform in time. So this was somehow the remainder term where we had to do something else, or we had to come up with a new idea how to estimate that, because the standard techniques seem to get bounds which are too bad. And the idea how to improve was to use the fact that, in fact, we can estimate this one here better by using that we apply it here to these Bogoliubov dynamics. And as I was saying before, we actually know a lot about these Bogoliubov dynamics. So we know how to compute the action of the Bogoliubov dynamics on creation annihilation operators. So instead of estimating this guy here, what we want to do is to compute it and afterwards do better in estimating it. And that's the idea, that simply some notation, that we want to now, instead of estimating it, we want to actually compute this guy here, so the remainder from the slide before. And how to do this is simply by using the properties of the Bogoliubov transform. So we know how the conjugation of creation annihilation operators with these Bogoliubov dynamics, how it looks like. Namely, it was exactly this rotation with respect to these operators gamma and sigma. So now we get for all these 4 creation annihilation operators, we get the sum for all the terms of creation annihilation operators rotated with gamma and sigma. This looks complicated, but I mean, we can compute what this guy is, because we always know that, first of all, an annihilation operator on the vacuum vanishes, and whenever we have a creation operator on the vacuum, the idea is to simply commute it through to the other side. So let's have a look, for example, at the guy that is where we have 4 sigma. So here we have A of sigma multiplying with A of sigma with A star of sigma and another A star of sigma, simply using the commutation relation. Right. So this one here, and using the commutation relations, we can actually compute it. So the idea is that we want to commute this one here through to that such that it hits this vacuum. The same here, and the other one we want to put to the other side. So what we get is the following expression here. So we get what we had before, and then here we have the scalar product of sigma tx with sigma ty squared, and the norm squared of sigma ty and sigma tx. Right. So we have to estimate, or the hope is that we can estimate this whole guy here by something that is uniform in time. But since we still have to do a time integral here, what we need in order to conclude that this is uniform in time is some decay of sigma t. And this was our crucial idea, that in fact we wanted to prove some dispersive estimates for these sigma t, so for these symplectic Bogoliubov dynamics. And this is the next theorem that was the crucial theorem and the crucial ingredient to get these uniform in time estimates for the many-body Bogoliubov approximation. And this is the following statement here. Namely, we consider these L infinity times L2 norm of the operator sigma, and then we were able to prove that in fact it decays in time as 1 over t minus s to the 3 half. So it's, if you still remember, the same time decay one gets for the Hartree equation. And what we needed to prove that are, again, the same assumptions we also had in the main theorem. The reason why we had it in the main theorem was because we used these theorem to prove it. And again, most of the assumptions are to ensure that we can actually use the dispersive estimates for the Hartree solution that were proven by Bogoliubov and Macedon. But we had to put these additional assumption that V is in C2 to close the arguments here. Also, let me mention that there had been earlier works that also realized basically that in order to improve timescales, one has to understand better the symplectic Bogoliubov dynamics. So these were these works of Bogoliubov, Macedon, and Napier-Kosky I mentioned before, who were able to lift the timescales from logarithmic in n to square root n. However, both of them did it differently because they considered the L2 times L2 norm of sigma. So instead here we considered the L infinity times L2 norm of sigma. And they were only able to prove that this norm is logarithmic in t. So they were not really able to show that there's some time decay here, which we were in the end. Right. Also, let me remark that in order to conclude with our dispersive estimates here, we also needed to have some control of these L2 times L2 norm of sigma, and we needed to improve that. So they proved that this scale is logarithmic in t, and we were able to prove that this is in fact uniform in time. Okay. I still have a few minutes left, so let me maybe at least quickly comment on how we prove these dispersive estimates. Right, okay, so before, it seems I wanted to mention again that right. So what is new is that we get these dispersive estimates, and what we need for that is, but I think I already mentioned that we needed some more assumptions on the potential, that it is C2 and not on C1, right? So for the idea of the proof, I think so what we did is to use or at least to follow ideas of that seem to be standard for proving dispersive estimates. And our idea was that, in fact, from the symplectic Bogoliubov dynamics theta I was showing some slides before, one can actually read off an PDE for the time evolution of sigma itself, and that's the following here. So one can see that, I think I forgot a minus sign here, that the time evolution is given by the Laplacian, and then there's these part here that comes from the Hartree evolution, and these operator K1 and times sigma, and then one has another term that that comes with this operator K2 multiplied with the second operator gamma. Right. One also gets another or a similar evolution equation also for gamma. So basically one can read off a coupled system of differential equations both for gamma and sigma, which we both need, but I will base my arguments now mostly of the one for sigma. And the idea now is to use again Duhamel's formula, and we rewrite sigma as the time integral over e to the minus I t minus tau, the Laplacian acting on the first variable, and then of all these terms, the three terms of the right-hand side. So these are all the three lines here. So that's very standard for proving dispersive estimates. And now the idea is the following, namely to use that one has these or one knows how the Laplace operator behaves, right? And to do right before we need to do the first step, namely what we wanted to estimate, or this was also one part of our novel idea, was to use these very special norms, so these L infinity L2 norm, and then use properties of the Laplace operator. For technical reasons, one has to separate two regimes. So we have to integrate first from S to T0, and which is chosen to be the maximum of S and T minus 1, and second between T0 and T. And for small times, the idea is to use the decay of the Laplacian. So to use that e to the minus I t minus t of the Laplacian actually decays as 1 over t to the 3/2. So in all these three terms, we use that we can estimate these L infinity L1 norm by gaining these prefactor here and estimating it by the L1 L2 norm. But one can also already see from this estimate here that we can only do this not up to t, because then we get a problem with the singularity here. So for that reason, we have to restrict to times up to t0 and do something else for larger times. And the idea there is that for larger times, we control all the terms of the right-hand side simply by these L2 norm of sigma, or the Laplace applied to sigma in the L2 norm, and also the operator eta, which is the operator gamma minus delta. So this is more a technical part. And also, so about this second time integral, let me maybe comment about that usually for dispersive estimates, how to close the argument for the second part is to use smallness either of the initial datum or of the potential. And this we did not have to do because we could use the dispersive estimates of the Hartree equation, because you can see that in some sense all the operators that appear here somehow depend on the Hartree equation phi t. So for us it was enough to use the dispersive estimates, and we did not need additional smallness here. Right, and with that we were able to conclude the dispersive estimate I showed on the slide before. Right, and maybe as a small outlook, let me maybe give another comment about what is simply corollary about the last two results you just saw. So about these uniform time approximation of the fluctuation vector, fluctuation dynamics by the Bogoliubov dynamics and the dispersive behavior of the Bogoliubov dynamic itself. And that's the following theorem, namely that we can approximate these excitation vector for times which are large enough, so on times which are bigger than n squared, by the free dynamics, which you can see here, applied to a state that is like that is u t0 omega. So it's a state that is a Bogoliubov state up to times t0, which you can see here. And starting then from t0, it behaves like a free particle, which means that for large times, so for times which are n squared, the Bogoliubov dynamic itself is approximated by free dynamics. So this is basically what we, which is simply a consequence of the previous two theorem. And this somehow also led us to the questions that we are still interested or still studying and discussing about what we can say more about, starting from this, about the long time behavior of fluctuations and what we can learn from that. Right. So with that, I would like to thank you for your attention and yes.
Okay, thank you very much for a very clear and interesting talk. Are there any questions or comments?
Yes, I have a question concerning the definition of these operators K1 and K2 on page 6. Maybe you can show them.
Yes.
Yeah. So if I look at this definition down here, what's the difference between these two? Or is this just a typo somewhere?
Exactly. Thanks a lot for the question. So there's a typo. There should be a bar here. So K1 is v of x minus y, and then there should be a bar over phi t of x and not with phi t of y.
Because this relates to alpha and the sigma or this gamma. What did you call it?
Gamma and sigma.
And sigma,
yes.
yeah. Mm.
Exactly.
Okay. Mm.
Thanks.
Any other questions?
I have a question, if I may.
Yes.
Where is the hypothesis of the positivity of the potential used in your estimates?
So in the estimates I showed, we don't need it, but in order to prove these dispersive estimates for the Hartree equation, they use the positivity of the potential.
Okay.
So,
Okay.
and because like our, like especially the part about the symplectic, so about the dispersive behavior of the symplectic Bogoliubov dynamics, there we heavily rely on the fact that we do have already dispersive estimates for the Hartree equation. And this is where like indirectly somehow we use also that one.
Okay, thank you.
Thanks.
Okay, any other questions or remarks?
Well, can I ask one more question?
Sure, sure.
Concerning this approximation of the Bogoliubov dynamics by the free dynamics. Is this essential that you have this compact support of the potential? I mean, if you have that, intuitively, I would understand that very easily. If you have n squared particles, the worst case is that they don't see each other then after a fixed time.
Yes, I don't know. For me, it's still hard to get a physical intuition about this idea that after, like, it seems like after n squared times, right, they don't see each other, they escape, it seems, somehow.
Yeah.
Right. But
that's the worst case when they are all sort of on a line, I guess, right?
I guess so, yes. But let's say for us, it was surprising to get that as a corollary, basically, that it seems that for large times, even Bogoliubov dynamics.
So, but I mean, if you don't have compact support, you would still expect it, or?
That's a good question. I don't know. Like from the technical point of view, again, I think we need it for these dispersive estimates. Otherwise, we cannot prove it. From the physical perspective, I don't know. Maybe even from a physical perspective, you're right, and then one would not expect that to be true. So.
Okay, but maybe let me ask the following question. I was a bit surprised in the end what you said, but you estimate, instead of estimating certain terms, you can compute them completely. So I am wondering where is the interacting dynamics? Is it still there or was it gone earlier? Because in scattering theory, you always have this interacting dynamics somewhere which you cannot compute. So how you got rid of it?
Oh, you're totally right. So I was lying a bit, but you found my lie. And so that was that I said that we compute that guy here, which is not true, because as you were saying, what we did compute on the next slide was this guy, but you saw on the previous slide here was still the interacting dynamics.
Yeah, okay.
So I lied a bit. So what we are able to compute is this one here. And then playing some tricks, somehow we estimate the remaining part, but we are not able to compute exactly the interacting dynamics. So this leads to, I mean, this was only a sketch of the idea, but like in order to apply this, we have to do stuff, basically. You're right.
Okay. So it's still there.
Yes.
Okay. Any other questions, comments? Does not seem to be the case. Then let's thank the speaker again and stop the recording.